calculations I did for the absorption of carbon dioxide on massive ammonia iodide perovskite surface. So my calculation is based on ozone-baked phase massive ammonia lead iodide perovskite. So our initial geometry is obtained from crystallographic data. The problem with crystallographic data is there is no hydrogen. So I need to artificially insert hydrogen into our simulation cell and then run geometry optimizations. So this is my simulation cell, the box. So our calculations is done in WASP, so under periodic boundary conditions. So it is infinite around all three directions. So here is a figure, shows the geometry viewed along different axes. So once we have the unit cell, we can just create a surface. Here I use the 001 surface as an example. So actually, we can just cut the crystal or split the crystal into half. By doing that, we end up with two kinds of models. We have a top model and we have bottom model. So this after doing that, we can just add 15 angstrom vacuum along the axis. So by this way, we can have our surface model. And also, next step is doing geometry optimizations. By doing geometry optimization, I fix the bottom 24 atoms, and all other atoms, like here, are allowed to relax during the geometry optimization. So, any questions so far?
What is that box? There's a large square somewhere.
Okay.
There's a large square shown which is half empty. What's the purpose for that?
You mean
Yeah,
right here?
that box. Why is it?
Here is just a vacuum. So we have 15 angstrom vacuum here. And here, this yellow box means atoms inside this box is fixed.
So both top and bottom have the same surface termination?
I guess for this specific...
You are the only participant in the conference.
For this specific surface, the top and bottom are very similar, but since it can be different for other surfaces. Like for this surface, if we split this model into half, then it is very different, right?
Mm-hmm.
But what is the z direction now? And what is the perpendicular direction to the surface? So if that is the surface, I don't understand the picture. Where is the z?
This is the z-axis.
Z-axis. But then it's not a surface, right? That is
This is just a crystal structure.
it's a slab
But
or something.
from here, for this unit cell, we can just cut it. Here is the surface.
What do you call a surface? Is maybe the question. You're cutting in the crystal or not?
So I guess it's just the name of Miller index. So if I have a 001 surface, that means the z-axis is
But do we
perpendicular to the
top of the
surface.
surface, or is that a side view? Top view or side view?
This
So
is the
that
side
top-
view.
What?
This is the side view.
That is what's a side view?
Yes.
But then that is not how we draw a surface usually. At least a surface chemist wouldn't draw a surface like that.
So teach us, tell us how do you draw the
But
surface?
he is cutting into the bark or not in that picture? It shows 3 layers or something.
Yes, it is 3 layers, yes.
Yeah, but that's not what we call a surface, right? The surface, that's a surface. You are cutting into a crystal, right? But the top layer would be the surface, right? Or not?
Well, it is a 3-dimensional set of atomic coordinates which we work with. And from which angle a human is looking at, it is a very secondary thing.
You can cut different surfaces, obviously, but
What is periodic boundary conditions on your point of view?
along the surface, I would have periodic boundary conditions.
Yes. So can you see periodic boundary conditions in this image, or can you understand how it is implemented?
Not really.
Okay, then let's ask speaker to explain it. So
Okay, so here the c-axis is like perpendicular to the surface,
Okay.
and along a-axis and b-axis it is infinite.
So that the left picture is a cut through the surface, right? Basically, if I understand that correctly.
I didn't get you. Can you say it again?
You're not looking on top of the surface, you're looking from the side. That's
Yes,
a
I'm looking from side.
cut through, okay. So what I would call a surface is the top layer of that picture. That is what we usually call a surface.
I can maybe show you another picture. Maybe you like this one better?
That is a top view or what?
Yes, this is a top view.
That's what we would usually call a surface in surface science.
But
at least.
it's
They are
it's the
same
same stuff, but view at different angles, right? It doesn't matter, right?
See what?
So, what is going on in calculations, in simulations? There is a set of Cartesian coordinates of each atom, right? And we can rotate the model and look on it from different angles. You are telling that you feel more comfortable to look from the top, but the angle human is looking at the model doesn't change the model.
This is
Your question is about visualization.
not only, I guess. So if we do calculations, do we take the bike into account? Apparently you do. Otherwise the picture wouldn't make sense, right? So you're not just looking at surface atoms in your calculation, apparently you're looking at the bulk also. That-
Yes and no. Let me explain, then we will be on the same page.
Okay.
Bulk is a structure that is periodic in 3 dimensions, in X, Y, and Z.
Yeah.
We are limited in computational resources, so we cannot have infinite thickness. So in this software, we have a box that is showed by this box, and it is replicated infinite number of times in each direction, X, Y, and Z. So if you do not put a vacuum on a top of thing that we call surface, and you do not want to call surface, if you do not put vacuum, empty spot, then it will be bulk. If you put vacuum, it will be a model of a surface. So in some sense, what we model is a infinite sandwich of thin films of finite thickness. If the results are not trustable, we can make each layer a little bit thicker, but it still will be infinite sandwich. Nothing else is possible. And side view helps us to see that we are not cheating and we provide enough vacuum.
So for me it looks like almost 4 layers or something. I don't know what the unit cell really is. Is that thing?
Yes, I would say there are just 2 layers here.
2 layers, okay. It would be misleading for a surface chemist to call that a surface.
We can work in a text to tell that it is visual representation of atomic model, side view. Do
Yeah,
not just do
you're
it.
cutting through the first surface shows the first 2 unit cells or something.
Yeah, we can work on the verbalization.
Okay, so I follow the same procedure for different, if it is not surface, then for different, what do you call it?
Let's call it surface for now. Otherwise, the speaker will be very confused and not be.
Yeah,
We called it surface for several years, and it is not. I know that you didn't call
but
it.
nobody else is calling it a surface, believe me. So, and I don't know if you put that in your papers like that. Because nobody is calling that a surface.
We'll work out the verbalization, but it is interface between area of space where there are some atoms and area of space where there are vacuum, there are no atoms. How you call it?
Its surface strictly is a two-dimensional layer, right? It has no third dimension simply. That is what we call a surface, right?
Yes.
And that thing has a third dimension. You picture. Right? We are going into the
Yes. But it is standard. It is the only way computational surface chemistry can be done.
I've seen cluster calculations.
Cluster is very not trustable. Cluster is a poor man's argument when it's nothing else is possible.
It's not that different, and that's a story. Yes, you use also a periodic boundary condition. Depends on how large you make a cluster. So you can call that also a cluster. If you like, you have a cluster with two units.
If you do a cluster,
in a way,
then there will be strain because side atoms of a cluster are not holded by scaffold of the of
the
anything.
boundary condition should take care of that. I mean, you're doing
Yes.
the same, right? That is not an infinitely large. That is also you have a certain number of atoms in your.
Yes.
So it is kind of a cluster. No? I mean,
No. Cluster is a group of atoms that is surrounded by vacuum from all.
but you use periodic boundary conditions. You have the same. You have a group of atoms which is surrounded by vacuum on top. So I don't know how you do the bottom boundary conditions.
So from this point of view, there is no novelty. It is like 1,000 people doing the same way. It is a standard approach. So it is no novelty in the way how the unit cells are prepared and how they are calculated. So it is.
Okay.
Okay, I will just call it surface, so otherwise it's really confusing. So basically I did the same thing for different surfaces. So I consider 1, 0, 0, 0, 1, 0, 0, 0, 1. So remember, every time we cut it, we have 2 models. So that means in total we have 6 models. And I calculated the total energy, and I found this one has the largest total energy. So in other words, this one is the most reactive one. So the following carbon dioxide absorption calculations is only based on this model. And here is some technical details for my calculations. Any questions so far? Okay, so for the carbon dioxide absorption, I just place the molecule at a different location of the surface, and then run geometry optimization and calculated the absorption energy according to this equation. So here, the hybrid means the carbon dioxide is bonded to the surface, and the surface, this term is just the surface itself, and this is the carbon dioxide molecule itself. So all these values are changed from geometry optimized model. So here, this is one specific configuration. So here I label the oxygen and the carbon and the metal distance is about 3 angstrom, and the carbon aldehyde distance is about 3.5 angstrom. This is a top view of this specific configuration. So actually, this one is the most stable one for my calculations. So,
And what is the mechanism? Why it is stable? Is there an explanation?
yeah, I guess at least for my understanding, so for perovskite surface, there are 3 bonding sites for carbon dioxide. The first one is the oxygen of carbon dioxide can bond to the metal, or the carbon itself can bond to the metal. The third scenario is the carbon itself can bond to the iodine. So in this case, the oxygen is bound to the metal. And there is some contribution by the carbon and iodine interaction.
So they have linear CO2.
Yes, it is linear.
Is that fixed, or do you change that geometry? Because most people believe that CO2 is not linear if it adsorbs on a surface. Right, there's the carboxylate story and so on.
For this specific configuration, so the initial geometry of carbon dioxide is linear, but in other examples, I did put band carbon dioxide into our model, but after geometry optimization, it is found the band is not stable. It will relax to the linear configuration.
So you do permit, you do allow geometry to relax
Yes.
for both adsorbate molecule and top layer of a surface.
Yes.
So to some sense, molecule seeks for most favorable place.
Yes.
The linear is a more that is very unusual to run, as far as I know the literature.
What are the angles between, like if you measure oxygen, carbon to oxygen, is it literally 180 or maybe there is some third digit deviation?
Like it's 0.5 degree
Okay.
from
But also the
Perfect
binding
linear.
you see is unusual, so something strange is going on. So maybe that's what it is.
We have other explanations. So why the experimental finding the binding energy is so large? We do have explanations for that.
Do you know which binding site has the most like stable, highest binding energy, like the lead and carbon dioxide, or the iodine, or what?
So right now I'm showing a perfect surface. So the largest binding energy is like 0.22 electron volts.
Okay. Oh. Is it with the lead side or the iodine side? Do you know which side?
Right now, my understanding is the carbon dioxide prefer the metal side
Okay.
instead of iodine.
Okay. Yeah.
And also it prefer oxygen instead of carbon.
Carbon. Okay.
And am I understanding right that the structure of the talk is will be you'll go over the table that at the left top?
Yes.
And each line of the table will be represented by additional slide in your presentation.
Yes.
So we should prepare to have at least 7 slides more. And they are printed here to follow you, so you can see on the screen.
Okay, here this figure shows the charge density difference. So basically, the yellow area means there is charge accumulation, and the gray means there is a charge depletion. So this figure tells if the carbon dioxide is actually bonded to the surface.
So it induces some perturbation to the charge.
Yes, like polarization.
Interesting.
So this is another configuration. So for this one,
And the line corresponding row in the table is highlighted with red.
yes,
Okay.
this is the absorption energy. So for this configuration, the carbon dioxide is stabilized by the hydrogen bonding of the methyl aluminum group. This is the one. So here the distance is like 3 angstrom. And from the charge density difference, we can say there is actually a bonding.
So it is closest to iodine or to the lead?
To the metal.
To the metal.
So you're trying out different absorption sites, basically?
Yes.
So how do you have, so you keep something fixed then, or how does it work?
No. I only kept the bottom atoms fixed.
But
So
why
it's like-
does the molecule not go to the best sites then automatically?
It's just that finding the local minimum instead of global minimum.
It looks pretty much like a stack calculation to me, what you're doing, but so it's not time resolved or something? Because
No,
last time we saw a movie.
Last time it was movie. This one is not time resolved. It is optimization.
Because a movie, the molecule will find by itself the absorption sites, then, I guess. If you do a time resolved.
When we do time resolved simulation, the molecule has freedom to explore different sites. It doesn't guarantee that it will explore all of them, but it can, due to thermal energy, it can overcome barriers between local minima. Here, because of the optimization procedure, if it is kept in a deep enough local minimum, it will not go out of there automatically. So human has to help.
So how do you force a molecule to go to specific sites then? In the calculation?
What do you mean by force?
You're choosing different sites. How
You
does
are
it-
the only participant in the conference.
I just randomly place them, provide them with initial geometry, and let them to relax to find their local minimum.
So you are trying different geometries, and upon optimization from random geometries, it stabilizes in like 7 possible geometries.
Yes.
So you use different starting conditions.
Yes.
Okay.
What is here? It's also carbon to the metal.
Yes. I believe for this one, so the initial geometry of carbon dioxide is like binding, so the carbon is bound to the metal, but after geometry optimization, it's just reformed to the linear configuration. So that means,
So the most stable is the most negative one then? Or?
yes, most stable is the most negative one. Okay, so for this one, this is a carbon bound to the iodine. This is a absorption energy is very low. So that means metal is a more preferred site than the iodine. This is just another configuration. It's also carbon bound to the iodine. And from charge density difference, there is actually some bonding.
So what could serve as a reference point? What are the, do you know, typical binding energies of carbon dioxide to another crystal containing lead? Maybe like crystal of lead iodide or...
And nobody has done that as far as I know.
Okay, so we do not have reference point to compare with. We only
That
achieve
is
conversion.
actually discussed on the paper, yeah. If you would read it. So there's nothing really close to that as when people looked at metal oxides, they looked at metal surfaces, right? But that kind of thing has never been done before, as far as I know. There are perovskite oxides of some sort. There's some literature for that. But that is that has also perovskite structure apparently. But
Perovskite is any structure with 3 type of ions.
yeah, so
And one can, they're very popular with, instead of iodine, there are oxygens, and instead of methyl ammonium and lead, there are like manganese and lanthanum or titanium.
yeah, so that kind of stuff has been done.
But they have no connection to here. It's different.
Yeah, that's kind of closest. At least they call it also perovskite, right? At least it carries the same name. Kind of.
But there are studies of carbon dioxide adsorption to this oxygen-based perovskites.
Yeah, yes, I think, so, but not kinetics, I think. I haven't really looked systematically for that. I have 2 papers or so, and I think that's kind of infrared stuff. And it's usually powders, I think. It's not really surface. Some kind of powder samples and infrared spectroscopy. So we can find something like that, but binding energies, I have not seen any binding energies. So usually CO2 dissolves below 200 Kelvin or so, unless it forms a carbonate, and then they have these bent intermediates. I think the bent stuff has to do with the carbonate formation, and because you do not form carbonates here, I guess. That's why you don't see any bent structures, I would guess.
Let's wait for
You form carbonates.
Let's look for.
But you need an oxygen, right, for that, or not? There's oxygen then. But, okay. So what is the most stable is the top 1 position? And what was that again, actually? The first one, is the...
So oxygen is above lead and carbon is above iodine.
Yes.
So there's some kind of multi-site adsorption things. As you call it, there's a name for that. There are examples like that are in the literature actually. So where CO2 is absorbed on more than one adsorption site at the same time, basically. Right, that looks like.
Yes, if you look at this picture, there's some binding.
I think there are examples for that in the literature, for that kind of geometry. But I think also basically the systems are not really on surfaces. I sent you a review 2 weeks ago.
Yep.
And that review has stuff like that is mentioned in that review. But I think these are powder samples also. I don't remember what kind of stuff that was.
So what kind of interaction is the OPV bond? Is it like partial covalent, or is it just some sort of dipole interaction?
Guess maybe I need to check the orbitals.
Because you did the optimization with the van der Waals.
Yes.
Okay, so the carbon iodine is probably just some sort of dipole.
But 20-something kJ per mole is not very large actually, right? So what temperature that is not 7,600 Kelvin?
You sent slides with conversion of binding energy into desorption temperature, but it is a little yet confusing because it is not simple conversion with Boltzmann temperature. This literally converting, it would be like over 1,000 Kelvin. It's the conversion is not direct as you show in your slides.
That's strange.
Like thermal 300 Kelvin is 0.027 Kelvin.
You are the only participant in the conference.
So it is like 10 times smaller.
Maybe uses schematics, right? You need a pre-exponential in our case. So we would like to have the desorption rates, and you need the binding energy and the pre-exponential. For an Arrhenius kind of, and I think our binding energies are much larger than 20-some kJ.
I remember in the paper you mentioned
We
170.
use the standard phrase, but nobody really knows what the pre-exponential is either, right? So I don't know how to compare. When your time absorbed stuff look pretty similar to the experimental, but that number here is too small, I'm afraid.
We need to work together on converting these numbers and desorption temperature.
So if you use a standard pre-expenditure factor, then 20 kJ per mole at 200 Kelvin or something, I would guess. That is pretty much standard CO2 adsorption kinetics. That is not consistent with our 700 something, 600, I'm afraid. That is pretty close to a normal, whatever, and any other surface.
So if it is the case, then one of us is wrong.
But that is not consistent with your movie, because your movie had a desorption temperature of 400 Kelvin something. That is not 400 Kelvin yet. So something is not consistent in your calculations. But I haven't plugged in the numbers. If you use a red hat, I don't know. Maybe you can do that.
I have to think about it.
If you use a standard pre-exponential and 20 kJ per mole, what is the desorption temperature? I think it's pretty low, but I haven't done the.
We have to wait and see.
You have to plug it in the equation, right? So, I'm afraid it's too low. Way too low.
So we need one more meeting for. Previous meeting was experimental results. This meeting is theoretical results. Another one will be comparison.
That is a tough one, yeah.
Or, yes, but we need to get through this red hat, or how you call it.
That is simple kinetics. But nobody knows what the pre-exponential, whatever pre-exponentially you use, this kind of thing. Because what we measure is a rate, right? The desorption rate, basically, which is a combination of pre-exponential and binding energy. If you have an Arrhenius, I don't know if you can calculate pre-exponentials if you do a dynamic calculation. Somehow there's a way to do that, right?
Possible, but I'm not yet ready to answer right away.
It's a different theory, I guess.
It could be. It's not a standard thing to do. It could be a challenge to.
Transition state theory, basically, right? Somehow DFT version of transition state theory or something.
It does exist.
Yeah, the question. It has a name actually, right? I have done it classically. In the dynamics class, it's a kind of theory. KLMN something theory.
Oh. I don't remember the name. I remember that.
That is a quantum mechanical version of transition state theory, kind of, which I never really understood completely.
We will have a chance. We will try. And now it will be new chapter.
Yeah. So I guess this chapter may seem to be interesting. So previously I consider a perfect surface. So what I'm doing right now is I create some defect surface. So I actually remove a mesoammonia here and iodine here. So suppose we have a decomposed sample, right? So by doing that, we end up with this structure. So we'll do some carbon dioxide absorption on this model. So I can also remove iodine inside the surface. That means we have cavity. So we have this kind of structure. This is a cavity. And here is our result. So this is one configuration. And if I for this model, the defect is on the surface. So the absorption energy is pretty low. It's like 0.1 electron volts.
It seems to be smaller than bits, so it's the binding on defects has a smaller absorption energy than
Yes, so this one is not good.
as most people believe that defects is giving you by a larger binding energy.
Yes, this is for the surface defects one, but we have some good data on cavity defects one.
Yeah, that's a different,
So here is our cavity defects. So here the carbon dioxide has some interactions with true lead atom. So the absorption energy is like 0.2 electronvolts. It's pretty close to our perfect sample. Now I tried different configurations.
So what you're showing, it is a hole drilled in the surface, and you put adsorbate there.
Yes.
Okay.
So for this one, like 0.4 electronvolts.
Mm-hmm.
Okay.
Okay.
Charge density.
So it interacts with to each side.
Yes.
The RAM. Okay.
And this is our most stable one. There is a slight difference with previous configuration. So here the absorption energy is 0.43 electronvolts.
Mhm.
It's like twice the
So
perfect.
it looks better, yeah, 40 something. Coming closer to the experimental, I guess.
So if you believe what we have seen by now, it means that to the clean surface there will be no adsorption, or adsorption of carbon dioxide to clean surface will be unstable and easily dissolved. But if the surface is defected with dips and kinks, it may explain that it stays adsorbed for at higher temperatures.
20 is not really unstable. 20 casual or more, that's what you had before. That was
20.
It's pretty standard binding energy, I think.
Mm-hmm.
But yeah. I'm afraid we're even higher than 40, but that is closer to the experimental. I actually put the numbers in the paper, but I don't remember.
We'll do another meeting for putting maybe two figures side by side or two numbers side by side. Okay.
So what was the difference with the last slide for the geometry?
Can say it's a slightly difference. If you see here, it's like perpendicular. So here there is some slight
Oh.
angle.
These are really complicated pictures for me at least.
Not only for you, for everyone. But
Where is the CO2 now? Is that somewhere? I don't even see it. Ah, that is okay.
so it's right above the methyl ammonium.
Yes, looking from this angle.
Okay.
And are those bond lengths about the same as the lead iodide bond lengths? The 3.35? They look about similar.
Slightly larger. Okay, it's 3.29.
So why is the binding now stronger? Is there any what is the electronic structure explanation for?
Well, there is a mechanical explanation that if the molecule feels the surface only from one side, compared to if we put it inside a cavity and it interacts with the walls of this.
Okay.
Even for a smooth surface, can some carbon dioxide molecule go inside the cavity, like, so it has some kind of a porous like structure, so can
Yes.
it penetrate through the pore and bound like a strong?
If one assumes that there is a pore, then carbon dioxide can fill this pore. And we do not know what is going on the surface. If it is not absolutely perfect, and it's hard to have absolutely perfect, there could be different geometries of defects, including this one. This one is a guess, but maybe not the worst one.
Okay, so we have another chapter. So,
80 is getting larger. Oh, that's 80. Wow.
so
That looks pretty close to our experiment.
And also we have water absorbed on the surface, so
Okay.
it's kind of a good explanation.
yeah, so I just assume there is some chemical.
Yeah, we have plenty
reactions
of
going
water
on.
dissolving during the thermal desorption, so we have water absorbed when we are doing the synthesis in atmospheric conditions. So
Okay, so it is
it's
possible.
close. Yeah.
Okay, so this is our chemical reactions. So, and this is just for the surface defect sample. So, I should mention for this value, I use the first equation. So here is the neutral carbon dioxide, and this is neutral water.
So how's that thing called? It's not a carbonate, right? There's a name for that.
Bicarbonate.
Bicarbonate or something like that, yeah.
Yeah,
So you assume that the surface has some water and carbon dioxide interacts with it and dissociates.
yes, in some way, just water stabilize the carbon dioxide by chemical reactions. Once we have chemical reactions, we have charged species, and these charged species are more likely to be resolved than the neutral.
Mm-hmm.
I saw one paper from pretty old on platinum or something where they came up with a similar thing. Experimental paper, right, from
Mhm.
90s or something. So CO2 doesn't really absorb on platinum apparently. Then they co-dose water and then it suddenly so it absorbs. So it increases lots of binding energy on a pretty inert surface. I guess people would believe that's correct, yeah.
Okay, so this is just another configuration. And so this is for the cavity defense one. So as we can see, the absorption energy is pretty large.
Guess we can get it larger like so what is that now? Water inside or
But still, we have the chemical reactions. So this is our.
Oh, so you had two approaches. First, or even four. First, put carbon dioxide on a flat surface. It didn't work. Then drill a hole, defect, and put carbon dioxide into a hole. Then third approach, assume that there is a water and water will interact with carbon dioxide to form this bicarbonate. And then it almost solves the problem. And then you combined approach number 2 and approach number 3, where water and carbon dioxide interact, and the surface has a defect in the form of a cavity, and this bicarbonate dips into this defect.
Yes.
Okay.
so now how to condense that in 5 pictures and 10 pages?
We have introduction.
Because we have 50 pictures, right?
Oh, dump everything into supporting information.
Yeah.
But we have a big intellectual challenge to select which of those data and which of those pictures are most informative and most corresponding to experiment. We need to select champion geometry.
I would not put everything in supporting, but you would like to write more than one paper, I guess. So it would be smart and not to put too much in the first. That is kind of the tricky always. You have just to put enough in that is accepted, right? But you have enough left over for the next paper. This is kind of the.
It's interesting.
So we'll write a letter and we can write a full paper about it.
Interesting strategy.
Yeah, well, that's what people do, right? Usually, I mean, that's how people do it.
Yes. But right now we should decide what.
Yeah, we have to compare the binding energies.
Compare binding energies and select the best geometries. Maybe if there are 4 chapters, maybe select only one geometry out of each 4. What do you think?
That is too much for a letter. I'm afraid, because they have 4 pictures. We have also experimental, right? I don't know how many we need. We have to show a TDS drive at least. So, maybe an OJ TDS. So 2 experimental and 2 theory. I would only show the geometry which gives the best match, I guess. And then make the table with the rest or something. And the detailed discussion you can put in a longer paper. But you may want to put it by yourself. You just write a theory paper by yourself, which has all the details. And then we just write one joint shorter paper. Something like that. Might be if you go in all the details, then you need 10 pictures or something like that. I guess. Yeah, I'm not sure what is the best vegetable experiment.
It's your homework
Okay.
to decide which of them is the best match to.
So what was the temperature? So we have one that depends also on concentration, right? It was going from 400 to 600 Kelvin or something.
So at higher concentrations, we see carbon dioxide desorption start around 400, as I remember, and at lower concentrations of carbon dioxide, so carbon dioxide can go and bind to the most preferred sites. So at lower concentrations, we see some kind of high temperature desorption starting around 500 or somewhere around there. So
Good. I had a question to collaborators. So suppose that we have several binding sites, as we saw in the first chapter, and they are not very different in absorption energies. They're kind of a little small, a little higher, but not drastically. So if you start ramping temperature on such a sample, where there are several binding sites, what is more probable, that adsorbate will desorb from one side, from another one, or adsorbate will activate and start browsing, going from one side to another side, and start actually desorb when it reaches the highest binding energy?
I think diffusion is much faster than our ramping.
So diffusion is fast.
Yeah, it's much faster than
So
the
if-
temperature ramping or anything.
So if you have like 7 different types of binding sites, it doesn't mean that you will have 7 peaks in desorption spectrum.
You would, yeah. But I
Only the
guess-
highest one will give the peak in desorption spectrum.
No, you would see all 7. So they're so fast that you are always in equilibrium, basically. Diffusion is so fast that you're kind of in equilibrium. So you would see thermodynamic equilibrium distribution. So it depends on the coverage, right?
Mhm.
How much you put, so you will populate the highest binary sites first. If you have enough CO2, then you will populate the other sites. So if the surface is really saturated, then you would see all binding sites. And it will give you just one broad peak usually. I don't think we can separate the peaks. And your peaks are pretty broad also, right? So that is more than one absorption site, I guess.
if you have 2 different absorption sites with 2 distinctly large binding energies, then we could see 2 peaks, like condensation and the submono layer. But if we have very close binding sites, then we will get some kind of a broad peak, like in our case, I guess.
Okay.
Yeah, lots of better. So how does it compare with the movies? I think the movies, because the 400 Kelvin, that was the first case, right? The movie was for the clean surface, it's CO2. But the 400 Kelvin looks much larger than the 20 K joule you have here. I'm afraid.
So
So-
for systematic analysis, we have a challenge by numerical cost. So we cannot, like, there are about 20 geometries. If you decide to do movie thermal ramping for each of them, it will be too much numerical resources. We should select best, most interesting, and maybe repeat deeper analysis for
I
those.
thought the time resolved stuff will find automatically the best binding, so you need only one movie.
Well,
So depending on what
now,
kind of-
now on at least 4 movies for each chapter. For clean surface.
Okay.
But it is a really interesting question how movie and binding energies correspond. This I haven't seen detailed analysis of this correspondence in literature. It will be a new word.
But you get the disruption temperature in your movie kind of. It's trivial to convert that to a binding energy. You know? You would just do the red hat the other way around. They don't know the pre-exponential, right? That is the.
And pre-exponential that we can, if we plug in details of the simulation for the movie into your red hat equation, and you plug in data of your experimental ramping, it could be very different results because you ramp like a 1 degree per.
The heating is the thing.
And here we ramp it like 1,000,000 times quicker, or maybe even quicker than that.
Is that kind of calculation is more what I'm used to?
Yes, it is very well. It is a lot of work to prepare geometries, but calculations themselves are very standard and not challenging. It's a lot of work, but no challenge.
So why are you not calling it a cluster calculation? It looks like
What-
a cluster.
What do you call cluster calculation?
The people make some of the cluster and then they do kind of the same thing.
I'm
I
very
guess the boundary conditions are different somehow. How that is implemented?
well. Maybe in different communities there are different jargon, different colloquial languages, but in our sub-community, cluster means something isolated.
Yeah, but that is also an isolated group of.
No, this is not isolated. It's periodic.
Okay, it's a boundary condition there. That's the
Yes,
difference.
yes.
And that is a fairly large. How many atoms? That is a pretty large thing.
Almost 100 atoms.
Yeah, that
Similar
is
to-
really large. So
It's very it's standard. It's not.
that is standard. Okay. Because usually the clusters are much smaller than that here. Because of computational limitations.
If you do clusters, then there are surface effects. If the under-coordinated atoms are from each side,
Yeah.
and it brings a very big error to all measurements. Here, we since the sides are covered, we have periodic boundary conditions. It is nearby periodic condition serves as a scaffold. It holds geometry and prevents from.
I guess I don't understand the details of the. With the cluster guys also use periodic boundary conditions. So, but I guess it's not exactly the same. So, and then they usually do a calculation on smaller and larger clusters and compare. That is converging then usually that kind of stuff.
Well, here.
But that is a pretty large one, I would say, for what I've seen. I think the larger the things, the better. Yeah.
Yes.
So it looks like pretty large. So we have really fast computers, I guess.
This is not. Each individual calculation doesn't look something above average for the community. It's pretty standard.
Okay. Yeah, okay. It dates back 10 years when I looked at that. So when I had a postdoc, he did some cluster stuff here in my group, which is almost how many years ago? It must be almost 10 years. I think he had only 10 years.
For 20 atoms, one can do a lot. For 20 atoms, one can do a lot. Like movies, all observables and maybe run it on a PC. Or here it uses like 100 CPUs for 24 hours. And
So I can set to the experimental binding energy. Thank you very much. And email us. I think it's some
so we might want to we might try to do a table and put computed and observed binding energies nearby, and then we have a lot of computed and a lot of measured, and we do not know which of them align, because there could be systematic shift. Like if theory underestimates binding energy, then we can shift the table.
Yeah, we will not really get a quantitative match, right? Nobody expects that. And we have only two numbers, right? You have two measurements basically.
Yeah.
So it's not, so here's one that's small, 10 length, and the one that's 20 or something. So we have two numbers. That's we can give it. Otherwise you have to put in more samples and repeat experiments.
No, let's do something quick. What we can do.
So we have only two numbers.
If we want to get to one measurement, we have to like use one sample for one measurement, because after one thermal ramp the sample tend to destroy. So like for one measurement we need about a week, because we have to synthesize the sample, put it in the chamber, and we have to make the vacuum and do those kind of stuff.
At least a week.
At least a week.
Unfortunately, another pump died 2 weeks ago, so we have only one vacuum chamber running at the moment.
So there are objective challenges.
And I have not the money to buy new pumps.
Ask Santa Claus.
You have to ask Alka and
Are those expensive?
the second hand, you want 5,000 or something? Or what is
7,000.
Yeah, I haven't even looked at it.
For that 500 liters per second turbo.
7,000. There was an aircraft which was, the rotor came off, what, 4 weeks ago? I've seen it in the news. Some United Airlines or something, there's a rotor blade of the turbine was falling off and we went through a window of the aircraft. So something similar like that happened with our pump.
Okay.
The turbo pump is also a rotor basically, right? That's one of the rotors came off and killed entirely the pump basically. So you cannot fix it. So you have to buy a new pump basically.
So it's dangerous in your lab.
Well, we have it in a steel, right? So it's not.
Yeah, it's inside the steel, so it doesn't came out, but we could hear the noise, strange noise that turbine blades making. So
Yeah,
and
it's
it
safe
goes-
on the aircraft. It's not really safe, right? Because it's open, right? The turbine is open. If the thing is coming out, so one passenger was killed. Well, you have not heard about it? That was 4 weeks ago. I think.
Yeah.
That was all over CNN News. The broadcast, the passenger was killed, right? That went through the window in the aircraft. So, it made an emergency landing. But not. Yeah, same as our pump. So otherwise we could put in another sample relatively fast, but we have only one chamber left now. So, which makes it even more tricky. The advantage of theory, right? Yeah,
So when do we meet next time?
we have to figure out what pictures. Usually
Yes.
you write along the pictures, the paper is the easiest. You have to figure out 5 pictures. If you write a letter first, so what 5 pictures, 4 or 5 pictures should we put in that paper? Right.
And we need to agree which of this data are mostly correspond to the peaks in your TDS.
I would guess that it's pretty much the highest. I would guess the highest binding energy you have. takes 5 minutes. You can just do it in my office and email it in 10 minutes to you, and you have the. Right, so one was 400, the other 600 Kelvin. Just to calculate what's the binding energy for 400 using standard pre-exponential. Also, now that is a chemical reaction. So the binding energy is your molecular adsorption, desorption, right?
But when it is dissolving, like with carbonate, have an equilibrium with carbon dioxide and carbonate with water. So carbon dioxide have an equilibrium with water. So when it is dissolving, it forms the carbonate, and when it is when the equilibrium goes the other way, then it forms carbon dioxide. So carbonate is the aqueous form of carbon dioxide.
So that is really the binding energy of the.
Can you show? Yes. See, there are two equations: E adsorption and E adsorption prime. In the red box on the left top.
So that is not the activation energy for the reaction or something.
So one takes into account what Tina taught, that it desorbs and reforms back carbon dioxide and water. And this is the one that gives minus 0.9 electron volt adsorption. Another equation shows the desorption energy if bicarbonate and hydronium desorb without chemical reaction, and then the activation energy is like 10 times bigger.
Okay.
And also we see carbon dioxide and water dissolving at the same time in our TDS peaks. Similar kind of temperatures, they both dissolve at the same time, and intensities are a little bit closer to.
Mm-hmm.
Yeah, but it is not really related, so that's better.
So when the carbonate, if the carbonate is dissolving with forming carbon dioxide and water, then it can relate
okay.
to.
So it can be correlated. So
Yeah.
it is,
If that is correlated.
Yeah.
so it is chemical reaction and
Yeah.
But that gives you the smaller number, right?
the bigger number, this minus 7.4 electron volts, it is it looks too strange. And those molecules, even if they desorb, they are not stable. It is just a Gedanken experiment.
And also in the gas phase, carbonates are not much stable, I guess. They have usually carbon dioxide.
So what is now the state organ? So what is now the largest number here corresponds to what?
So there are 4 columns. First tells which model.
Okay.
Second tells the binding energy in electron volts corresponding to scenario that Tivan verbalized with chemical reaction of forming carbon dioxide and water upon desorption. Third column is the same binding energy converted into units of kilojoules per mole.
Okay.
And the fourth one is this abstract reaction when bicarbonate and hydronium desorb but do not perform chemical reaction.
Okay.
And hydronium and carbonate, those are somewhat like stable at the aqueous phases, not in the gas phases, as I
Mhm.
know.
Mm-hmm.
So that may be the reason for that. It's kind of not stable, unstable molecules of hydronium and carbonates at least in the gas phase.
But then that makes it more tricky to get an experimental number, right?
So with that, I guess the 86 kilojoules per mole may be close to our data values with water and carbon dioxide desorption with that reaction, chemical reaction.
Yeah, but then you cannot use the Rettet equation, wouldn't give you the correct number then, right? Rettet, that's just molecular adsorption, desorption. That is not molecular absorption, desorption then, right?
So it adsorbed and formed the chemical compound, whatever the carbonate,
Yeah.
and it desorbs as carbon dioxide and water.
Yeah, but that is a totally different process.
And we are detecting only the desorbed molecule, carbon dioxide and water. Adsorbed species we can detect, right?
That is more tricky.
Yeah. So we are detecting the desorbed species. So it can be adsorbed as the molecule forming the chemical bond and desorbed as the carbon dioxide and water, molecular desorption.
But that is dissociative desorption or something.
Yeah, anyway, like we are collecting the product as carbon dioxide. So we defined it as molecular adsorption because we didn't know those mechanisms or anything. But now I guess
Yeah, but how to calculate the experimental binding energy now? That is not a simple red hat. Right. The red hat is adsorption, desorption, but it's not what you're doing, right?
Here, well, I'm not expert in your red hat approach, but what do you understand? Maybe if I understand him correctly, one probably can consider this carbon dioxide plus H2O as just one bigger entity that we do not look inside. You have it adsorbed and desorbed, and then just as one unit.
You can also approximate it as first order,
Yeah.
because that is not first order kinetics, right?
yeah, it's not first.
And what the red hat is first order, right? And that is second order or something?
Yeah, it's second order.
The second order question.
Yeah, equations are different. Yeah,
It's a different story. There is a red hat for second order.
second order. But we haven't used that, right? We
No.
can look into that, I guess.
Yeah, I have to look. That takes more than 5 minutes. I'm afraid.
Yeah, usually we
Because we haven't
see
used
first
it,
order
right?
desorption, but this is second order.
We haven't used it very often. There is an equation for that also somehow. Now the pre-exponentials are totally different for second order. Right? Actually, nobody really knows what the pre-exponential is. That will be the tricky part, I guess. For Morkel adsorption, that is kind of a standard value for that. But for second order, I have no idea what's the pre-exponential. You can get any binding energy depending on what pre-exponential you use, right?
So no,
It makes it somewhat more tricky, this story.
But it looks interesting, I guess, the reaction and desorption.
Yeah, reactions
Yeah.
are always more interesting
Yeah.
than Morkel adsorption, I guess. So we can send you a first order approximation in 5 minutes. The rest takes longer, I'm afraid.
that's fine. That's fine. So that's maybe if you do not need to write reports on grants urgently,
I have no grants, so that is the advantage. I have no
okay,
grants.
then we will do everything quickly, but without extra rush. Maybe meet next time in like 2 weeks,
Yeah.
so that. And I need to travel, but this is video conference. I will just pop up on the screen.
And he knows how to do that.
We'll discuss. It's very easy.
Right.
Basically, you do nothing. You come and it works. There are tech support for these rooms.
Okay.
Okay, well then, many thanks for interesting collaboration and strong intellectual contributions.
The numbers are here on the small one.
You can have.
So meeting is dismissed.
Thank you.
Thank you. Thank you much. I don't know. I just made some comments, but
I have to find back some
comment for myself. Daniel? So you have an idea how to continue the project that you are doing?
Yeah.
Just follow what you want is doing.
Follow what he's doing.
In some sense, you got some inspiration looking at. You have so here it was hydronium and then bicarbonate, and you have different pair of anion and cation, and you can explore their binding energies.
Okay. Yeah. I saw that.
You don't need to drill the hole, just simple on the surface, and It's almost done. You have all components. You just analyze the data in similar way, more detail.
Yeah, I just have to redo some calculations because I lost them because they were
Yes.
on South Dakota
Yeah.
testing.
Those should be good.
Yeah, I can do that.
Okay. Yeah. Thank you.
I have some question about this
Yep.
configuration. So if we want to write a paper, we need to perform additional calculations. Because right now I just try two configurations, but actually you can have manually.
Let's wait until what they tell, because right now we didn't have intentions to make it our primary goal, and maybe we already have enough data for this collaborative paper. If you have inspiration and you want to do further, it is great, but I would think more, again, it's only ideas which can be wrong. Selecting most realistic or most interesting configuration and to do much deeper analysis of everything, and maybe look into optical properties because defects spoil any optical activity, or maybe do TD-SMD for looking if it will facilitate reactions. You saw the papers I sent last night.
Yes.
So that perovskites can facilitate reduction of dioxide. But it's not the ideas are not yet ready to do. It's just to think and discuss. Because without experimental data, just looking on surface geometries is not super competitive. If you go into more exotic or practically important properties, then yes, it doesn't need many geometries, just do some advanced analysis.
Do you buy this data?
They buy this data.
It looks suspicious, right?
Yes, but were you thinking of making molecular dynamics for this system and see if the reaction of recombining of hydronium and bicarbonate into water and I don't know if they need it for the paper, but it would be just cool and curious and to see reaction.
I guess I have one specific configuration. So the initial geometry is quite like this one, but
Mhm.
after geometry optimization, I say a hydrogen is transferred from here to here.
Mhm.
So here we have water, and we have H2CO3.
Okay, and
So it does make sense to me, because it seems the positive charge or the negative charge ions are more favorable than the neutral, right?
Mhm. Well, the H2CO3 is also not stable. It will it exists on only in solvents or on surface. So upon heating, it will decompose and dissolve. But again, I don't have a clear mind about it itself. Just searching for something of larger interest just than just finding energies. If you look for something that can work as a standalone paper without experiment, then it should be something brave and outstanding.
Okay. That's great.
Many thanks.
Thank you. So actually,
I may stop. I do not promise I may stop by just for a couple of minutes during the day, and then next time Tuesday, 4 p.m. I will make online meeting outside.
okay, you're
And-
traveling?
Yes, I'm going to DC for next week, and then for 3 weeks to Los Alamos, and we will see each other in Los Alamos, right?
Yeah. Okay. See you, Dr.
Yeah. See you.